Take a look at predicting the molecular ion peak in the region about the molecular ion peak given information about isotopes and their natural abundance. And what we're looking at here is the examination number 1 from 2202, Organic Chemistry 2 in 2019. This is question number 7, which reads, consider the fictional molecule, which is a methylene, a CH2, that is then attached to an atom X and an atom Y. That's it. And what we want to be able to predict is what's that molecular ion peak region going to look like. Now, we have some other information. It turns out that that atom Y, it really exists as a number of different isotopes. It could be 10, Y12, or Y14. So these different isotopes exist in a natural abundance in my fictitious world, and each of those exist at 33% natural abundance. Turns out that atom X also has 2 isotopes. Not also, it has 2 isotopes, which exist as 20 and 22, and they're in a 1-to-1 ratio as well. And so what does this mean then? If every single peak in a max spectrum is a finite weight, then what would the weight of a molecule of YCH2X be? Well, it turns out then that any molecule that could possibly possess these combinations of atoms would be a combination of molecule Y, its 10 isotope, attached to the methylene, attached to atom X with the 20 isotope, or the next molecule that comes flying down that mass spectrum would be a Y12 attached to that methylene and the 20 isotope of atom X. And then likewise, there's Y14 could be equally probable of finding coming flying down that mass spectrum to be measured. And the idea here is that this molecule will weigh 2 mass units less than this molecule, and this molecule will weigh 4 mass units less than the last molecule. But because all of these isotopes are naturally abundant, you don't get the average of them, you get one of any of them, and of those you would expect these 3 to be the potential molecules that could be formed. Or this extends a little farther, because the other possibility is that these Y10, Y12 atoms attached to this methylene are then attached to not the 20, but the 22 isotope of atom X. Interesting. Well, if that's so, beam of electrons coming down instrument, gets bombarded by electrons, picks up an electron to become the molecular ion peak, or maybe it loses an electron from a heteroatom to become a molecular ion peak. Of any one of these molecules that comes through, it has to be one of these variants, of which each of these variants then has a different molecular weight. And that molecular weight is going to be, 44 grams per mole, if I did that right. 46 grams per mole, or 48 grams per mole. Interesting. Then these over here weigh 46 grams per mole, 48 grams per mole, and 50 grams per mole. And so if we are to sketch the molecular ion peak area about this molecule, we would be placing peaks at 44. We would expect to see a peak at 46. We would expect to see a peak of 48 from these 3 atoms. we would expect to see, or molecules, we would expect to see a peak at 46 as well. Hey, check that out. We'd expect to see a peak at 48. Hey, check that out. So two different combinations of different atoms could add up to this 48, or isotopes add up to this 48. And then there's a 50 as well. Well, then how do we go about the last part of this, which is correctly drawing the peak height, because the peak height has everything to do with the relative abundance that is present? Well, for this, it's actually pretty easy. And in the solutions guide, solutions for this, I didn't necessarily illustrate this as well. But if this is 50, this is 100. So 50, let's move that up just a little bit more so I can be a little bit more precise. 100 up there. That looks about the same. And then we'll say 33 is roughly here. And 66 is roughly right in here, let's say. Yeah, it's a little off, but that's the idea. Well, then the contribution, let's play probability now. We said that Y10 exists at a relative 33% of the time for Y10. And so if I'm using a combination of Y10 in my molecule, so here's an instance of Y10, here's an instance of Y10, then I would expect 33% of the time, so here's my peak at 44, the height here is going to be represented by 33% of that, and then 33% of this. The natural abundance of this molecule, which is 33% for Y10, is coming from, the height then will be based on that 33%. Then for the X20, we know that that's going to appear at 50% of the time. And so 33 plus 50 would give me the relative peak height of that for a molecule of Y10 with this X20. Awesome. And then this X22 over here on the other side, that X22, that appears 50% of the time as well. And so we would expect a peak height that would look something like this, 50% on top of that 33%. And now we know the contribution to the overall peak height based on the 50% relative amount of this one, or the 50% relative amount of X20 combined with the 33% relative amount of Y10, or the 33%, or yeah, the 33% of Y10. And so let's extrapolate this a little bit more then. We would expect to see a peak at 46 that is the combination of Y12. So we haven't talked about Y12 yet, so let's just do this. Y12, which we know from the problem, is 33%. And so that's interesting. We would expect 33%. So this height, 33, we are going to run out of real estate real quick, but I'll fix that. Don't worry. And then the other contribution of that is coming from X20, which needs to be another 50% peak height. And so we'll just sneak this onto this other sheet of paper below it, the scrap piece, and say this 50% right here, we're going to add it right on top. Just like that. And now we have the relative peak height from the contribution of Y12 and X20 in this combination right here. Here's another Y12. Here's another, X22. We've already talked about that one. This peak would appear at 48, and it would consist of a 33% contribution from Y12 and a 50% contribution from X22. And let's just keep going. The only other thing we haven't talked about then is the Y14 peak. And so let's just give that a good old-fashioned Clemson purple for Y14. And that is going to be in combination with an X20. And so that's a 33 and 50 again. And that 3350 is going to appear at 48. So here's the 33 contribution. Here's the 50 contribution. And even though I have completely lost control of the page and this, what you should really be seeing is a 1:2 peak height ratio. Well, the last thing we have to talk about then is this Y14 that's now combined with an X22. We know the weight of that, so we can predict where the peak is. Now let's predict the peak height. And it comes from a 33% contribution from Y14. Yoink. And a 50% contribution from your X22. In a really nice mass spectrum. I don't know the exact heights. That's why I asked for the relative heights. And just to absolve myself of this mess on the paper, you'd really just expect to see that, based on each of those individual isotopic atoms and their relative amounts and weights. Hopefully this is helpful in assigning or sketching out a M+2, 3, 4, 5, whatever it may be, peak of isotopes in a mass spec. Good luck on your preparations.